A partial draft of this is at my website. It's not complete, but it's close, and it contains many of the ideas that I'm going to talk about today. And so here's an outline. This deals mostly with approximate policy iteration. So I'm going to start with that, and then I'm going to explain how it can be implemented with value and policy networks, neural networks, that is. Then I'm going to talk about some new ideas relating to parallelization. One is multi-agent rollout, and I'll explain what that means. Basically, the control consists of multiple components with one component corresponding to an agent, a separate agent. And then I'm going to talk about a more traditional form of parallelization, which is partitioning the state space and training in different parts of the space with communication between the processors. So, okay, let me start with AlphaZero. It's an amazing accomplishment. It plays much better than old chess programs, but most importantly, it plays different. It has discovered new ways to play an ancient game. I think that's very remarkable. Moreover, it has learned from scratch just the rules of the game, and after 4 hours of training, it could play as well as the best computer program, and after several days, it could play much better than that. And moreover, the algorithm that it used is portable because in particular, it learned how to play other games, such as Go, Shogi, and others. Okay, now the AlphaZero methodology is a very skillful implementation involving several ideas. The first idea is policy iteration, the fundamental dynamic programming idea of policy iteration, policy improvement. Start from a strategy, play the strategy, and improve the strategy, and do this repeatedly. Cost function approximations and policy approximations using neural networks. Massive parallelization. This 4 hours would translate to years of training had it not been for parallel computation. Finally, it involves some very skillful look-ahead approximations. In particular, the technique of Monte Carlo research has been very effective within the AlphaZero context. Now, what we will aim to do here is develop a methodology that relates to AlphaZero, contains several of these ideas, perhaps in modified form, but applies far more generally. So I'm going to start with the standard alpha discounted Markovian decision problem, where you have a stationary system and cost. The system evolves over an infinite number of stages. The system equation is what you see here. Xk is the state at time k. Uk is the control at time k. And Wk is a random disturbance. And we are considering policies that map states into control subject to some constraint. And at each stage, going from xk to xk plus 1, there is this cost here, which is discounted by a factor alpha. And the cost of a policy is obtained by adding up all those costs over a finite horizon, take their expected value, and then take the limit as the number of stages goes to infinity. And the optimal cost function is the minimum of this over all mu, over all policies. So it's a function. Depends on the initial state, and it's the main object that you're interested in, because if you know J star, then you can obtain an optimal policy by minimizing in the right-hand side of Bellman's equation. However, obtaining J star is extremely difficult for challenging problems. So we're going to work with approximations of that. Now, a very fundamental algorithm here is the policy iteration algorithm, where you start with some policy, which I'll be referring to as base policy, this mu. You evaluate that, you find a cost function, and then you do a policy improvement where you minimize in Bellman's equation with J mu instead of J star. And you obtain a new policy, which I'll be referring to as the rollout policy. So a base policy generates a rollout policy, and this process can be continued. And the fundamental policy improvement property is that the rollout policy is better uniformly than the previous policy. So this is what AlphaZero is also based, starting from a policy, a strategy, and improving it. Now, for the exact version of the problem, you have this policy, this property holding everywhere for all x. Now, there are many variants of policy iteration. Optimistic, where this where this policy evaluation has errors. As multi-step, instead of one-step look ahead, we use multi-step look ahead. You may operate with Q factors and so on. Our focus is going to be on approximate versions. Okay, so now policy iteration with approximation operates like in this figure. You start with a base policy, you evaluate it approximately, perhaps with something like a neural network, a value network. Then you improve it again approximately, and you approximate the corresponding policy with some policy network, and you obtain a rollout policy, and you keep going. Now, you don't get policy improvement here, but you get approximate policy improvement within some error bound. And there are a number of methodological issues to deal with here. The theoretical issues as error bounds, convergence guarantees, sampling efficiency. There are quite a few issues, and there are also very, very daunting implementation choices. What to approximate, how to sample, how to explore the space, how to train, implementations online versus offline, model-free implementations versus model-based, and so on. And there's no guarantee of success in this. There is no method that's good for all or even most problems. Instead, there are several different methods that you can try based on your theoretical understanding, your intuition to the problem, your experience, and hopefully something will work, okay? Now, as a mathematician, I find this not very satisfying, but I would not be honest if I didn't tell you that that's what's going on in reality. Our focus, now there's tremendous amount of computation involved in all this, and I will focus on how you speed up this computation through distributed and perhaps asynchronous computation. So I will focus on two types of distributed computation schemes. One is multi-agent parallelization and deals with large control spaces. And I'm going to focus on the case where the control has multiple components, like one component per agent. M can be fairly large here. And obviously, the size of the control space becomes enormous, and dealing with that in the context of one-step or multi-step look ahead is very difficult. The second type of parallelization is more of a standard type of parallelization, multiprocessor parallelization, and deals with large state spaces through partitioning. You cut down the space into pieces, and you train multiple value and policy networks 1% of the partition. Of course, these networks have to exchange values. They have to communicate with each other. Now, distributed computation dynamic programming goes way back. There are my papers from 82, 83, and it's treated quite extensively in the parallel distributed computation book that I wrote with John Stiglitz. I had a series of papers with Jenny Yu from 2010 to 14 on distributed policy iteration. These deal with value iteration. This deals with policy iteration. And there was an earlier paper by Williams and Bird, which motivated a lot of our work. A few months ago, I wrote a paper on multi-agent rollout. And just a couple of weeks ago, we finished a paper with Stephanie Gill and three of her students, Shushmita Bhattacharya, Sahil Badyal, and Tom Wheeler. This paper just appeared, and it's going to be published soon. Okay, so now let's get into this idea of value and policy networks. The standard scheme for approximation in value space involves using a cost function approximation j tilde in place of j star, the optimal cost function. And at a given state that you come into, you do this minimization. You form this expected value involving the cost of the first stage and the cost of the future appropriately discounted, and you can view this as a Q factor, okay? The approximate Q factor corresponding to a pair X and U. You minimize the Q factors over all U, and that gives you a control that you use at state X. Now there are three approximations here. One is j tilde in place of j star. This expected value can be quite expensive. You may wish to approximate this by some kind of limited simulation, for instance. And there's also the problem of simplifying the minimization operation, which can be, again, daunting. There are possibilities here, like discretizing the state space, a coarse grid, or the scheme that I'm going to be talking about shortly.
Do you at least know the G exactly?
I'm sorry?
Do you at least know G exactly?
G.
G, the first stage.
You may know it. You may know it, and if you know it, you should use it. On the other hand, this also applies to a model-free implementation, whereby you have, instead of having a model, you have a computer model. And you obtain samples of this G, and you approximate the expectation by doing simulation. And that's okay. I mean, there's quite a bit of work along this direction. But this scheme does not preclude a model-free implementation. Okay. Now, there's also the issue of how do we approximate policies. Okay, the rollout policy is obtained by one step look ahead, but how do we represent that? And the major way of doing that is to introduce a family of policies, a parametric family that depends on a parameter R, such, for example, a neural network, in which case R would be the set of weights of the neural network, and then you find some R here that somehow fits the situation. Okay. So now how do you go from value approximation from a j tilde to a parametric policy? Given j tilde, you can do one step look ahead and get training data, state control pairs that come from the rollout policy. And then you feed this into a classifier, which gives you a policy. Now, what do classifiers have to do with policies? Well, if you think about it, a policy is a classifier. Because if you have controls that take values, let's say A, B, C, then the policies have the form that to each state X, you classify it as being type A, type B, or type C. Okay? It's really the same problem. X is classified as type U if at state X we apply control U. And how do you train the rollout policy as a classifier? You generate a training set by doing this one-step look-ahead optimization with this j tilde. And for sample states XS, you obtain sample controls, and you collect a lot of sample pairs like that. And then you approximate the one-step look-ahead policy by feeding this sample set to a classifier and obtain an approximation. And in particular, one way of doing it is by least squares regression. It's a standard way of building classifiers, and there are other possibilities also.
Dimitri, for this, well, actually, not ask you questions. I have one now, I have two. Do you compute the expected value approximately from lots of samples, or does it, I guess, whatever you can do?
You do whatever you can do, yeah.
And then for the
whatever you can.
And for this last one, where you want to do a least squares fit, I guess it doesn't matter. You're saying run a classifier. That's what you're saying.
Run a classifier now. Okay, now an important point here is that this type of classifier will give you a randomized policy. It will give you probabilities of applying various controls at the corresponding states, okay? And what you have to do then is go through a max operation and put out at the output the control of maximum probability. But ordinarily, you'd use here a randomized policy. Yeah.
Wouldn't it be sensible to somehow take into account the suboptimality of the different actions that a policy may take? I mean, maybe a cost-sensitive classification objective would be more sensible, right? So if you have two actions which have similar future returns or values, then it's not a big mistake not to take one of them and take the other one.
There's a lot of methodology that underlies this. It's an oversimplified picture.
Okay.
Everything you know and love from classification theory can be applied here, and there are software that will do this in many different ways. You don't even have to use least squares regression here. And of course, if you do use least squares regression, you would also add a regularization function, perhaps, and so on. Okay. So all the tricks that come from classification theory apply here. Okay. So now, how do you go from policies to value functions? Basically, a policy has its cost function, and then a cost approximation can be obtained through truncated simulation. So we have a policy, and we have various initial states here, and we simulate that policy, generate a lot of simulation trajectories, and perhaps because the simulation trajectories can be very long, you truncate them and take some kind of heuristic cost function approximation. It may come from an earlier approximation. So how do we do this approximation? Well, for deterministic problems, we just run the policy from an initial state once, only once, because the problem is deterministic. And we accumulate the stage costs, and perhaps we truncate them at some point. For example, we set the rest of the cost to 0 because in view of discounting, this cost may be negligible. For stochastic problems, you have to do Monte Carlo simulation and run the policy from a given state many times and obtain the Monte Carlo average. And truncation is important here. In truncation, we simulate mu for a limited number of stages and neglect the cost of the remaining stages, or add some cost approximation at the end to compensate. Okay, so we have from values, we can go to policies, and from policies, we can go back to values with approximations. And all of this gives the scheme whereby, starting from a base policy, we collect value data, the previous slide, approximate its cost function, and fit a value network to that. And then we use that, we then obtain the samples of the rollout policy using that value. Then you approximate the policy with a policy network, and you obtain a new policy that can be used as the base policy for the new round of policy iteration. And now in the idealized case where there are no approximations, you have the cost improvement property. With approximations, the policy improvements approximate to within an error bound. And there are error bounds for this. And there are many variations of this scheme. Optimistic policy iteration, Q-learning, temporal differences, and so on. There are many algorithms that you can use in this box and in this box as well. And most reinforcement learning algorithms, including AlphaZero, use variations of this scheme. And some variations are highly optimistic, very little data between values and policy updates, and so on. There's a big range of methods that have been tried. Now the question is, how do we use parallelization and in this approximate policy iteration scheme? And you can think of 4 different types of parallelization. One is Q-factor parallelization. At the current state, you have to evaluate lots of Q factors, one for each possible control. However, these Q factors are independent from each other and can be computed in parallel. Okay? It's a naive kind of parallelization. AlphaZero has plenty of that it's obvious if you have parallel computation, you would want to do that. Monte Carlo parallelization. Of course, Monte Carlo simulation is highly parallelizable, and similarly, each of the Q-factor calculations involves, when the problem is stochastic, involves the computation of an expectation, and Monte Carlo simulation can be parallelized. Now, the third type is what I call multi-agent parallelization, and corresponds to the case where the control has m components. Therefore, the look-ahead minimization at x involves the computation of as many as n to the m Q factors. There is an exponential explosion of the number of factors that you compute. Even if these components take two values, let's say 0 and 1, still you have 2 to the m Q factors. And here is the maximum number of possible values. And what we will do is consider a scheme that reduces this computation dramatically to n times m, a dramatic reduction, while maintaining desirable properties of the scheme. The other is multiprocessor parallelization, where we use a state space partition. We execute separate value and policy approximations on each subset, and these approximations communicate with each other. So we'll focus on just these two and start with multi-agent rollout. And we aim to simplify and to parallelize the one-step look-ahead. Okay. This is a search and rescue problem, but to make it more interesting, I've turned it to a spiders and fly problem. You have 15 spiders moving on a grid along the 4 directions by 1 unit at most, and a fly that moves randomly. Now, the spiders have perfect vision. They know where each other are, and they also know where the fly is after it has completed a random motion at every step. So the control here is, of course, the joint motion of the spiders. It has 15 components. And the objective is to catch the fly in minimum time. Once the spider lands on top of the fly, then that's the end. And we want this to happen in minimum time. Now, if you try to do one-step look-ahead or a one-round rollout, a one round of policy iteration, it's impossible, because there are 5 to the 15 Q factors. Each spider can move in 4 directions, take where it is, has 5 choices, and the number of Q factors is extraordinary. Now, we're going to reformulate this one-step look-ahead problem in a way that maintains the cost improvement property, but the spiders move one at a time. They take turns in a given order and make a choice between 5 moves at each step. So the total number of moves is 75. 5 times 15. And what we're going to do is break down the control into a sequence of 15 components. And the theory behind this is the following. Actually, this idea is more than 20 years old. It appeared in the neurodynamic programming book that I wrote with John Tsiklis. It's a whole section there. And it deals with how do you trade off control space complexity with state space complexity. Reduce the complexity of the control space at the expense of increasing the complexity of the state space. And the way we do this is we unfold the control action into its n components. And we break down transition from xk to xk plus 1 into m little transitions, where we choose the first control at the first step, then knowing that we choose the second control, the third control, and so on. Now, the problem is reformulated. It's equivalent, okay, because control choice are made with knowledge of x. And the control space is simplified at the expense of introducing a more complicated state space and additional cost functions. Now, we apply the rollout one-step look-ahead idea to this problem. And the rollout algorithm is just the standard rollout algorithm for this problem. It's not the same, but it still maintains the cost improvement property. And moreover, the size, the increase in size of the state space does not adversely affect rollout. Rollout doesn't depend on how big your state space is. You move from one state to the next, and you do a one-step look-ahead calculation, and how big the state space is does not matter. And of course, the complexity reduction here is that the one-step look-ahead branching factor is reduced from exponential to linear, where n here is the number of possible choices of each component.
So there are m times more stages now. Because
M times more stages, yeah.
the state
Corresponds to m choices of control, one at a time, from a smaller
so there are
space.
intermediate states like xk superscript j, where j goes from 1 to m or something.
Right. If you were to calculate a cost function approximation, you would have a problem, because you would need to approximate all these huge functions. You could do it, but it is something to consider. It may be a daunting task. On the other hand, when we do one single policy iteration, we don't have to do that. Okay.
This like model, I mean, this feels like model predictive control a little bit, right?
I'm sorry.
This feels like model predictive control.
It feels
Model predictive control.
model predictive control.
It has a feeling like it's similar. The first you want is the one that really matters. The rest you play out, and then we update.
Well, rollout is contains a special case, model predictive control. It's a special case of rollout. So that they share the feature of landing at a state, doing a heuristic calculation, and then going forward to the next state and so on. It's all connected, but model predictive control ordinarily has an infinite control space. So this trick cannot be played easily. Okay.
Question. So it looks like your original problem has permutation symmetry in terms of your spiders, and that's another thing you can use for reduction. But by doing this type of unfolding, you are breaking the symmetry in the problem. Is there a comparison how you can do symmetry reduction versus this?
This is not exact. There's always approximation involved, right? So you don't expect to get an optimal solution here. The other thing, now that you mentioned permutations, the order here is assumed to be fixed. However, it could be part of the optimization. In other words, you can try several different orders at every step and see what works better.
Sequencing of those.
Oh, okay.
Okay. So I have a demo. It's the first time in my life that I've given a demo in a talk. It may or may not work. I have quite a few demos. If this doesn't work, I can show you privately, but hopefully it will work. And now this involves 4 spiders and 2 flies. And okay. So this is the base policy that I'm going to show you. Okay, there are 4 spiders and 2 flies. The flies move at random. And the base policy here is a naive heuristic, a shortest path heuristic, whereby the spiders act on their own, selfishly. Each one goes straight to the closest fly, regardless of what the others do. The spiders don't communicate. Now we're going to use this in a rollout and see whether the rollout scheme learns from the base policy. So let's see if this will work. I'm showing now the base policy. Oops. Okay, you see now that the spiders don't try to do anything smart. They all go to the closest, and this is a Manhattan distance that we're using here. And 2 of the spiders prefer the horizontal, and 2 of the spiders prefer the vertical. Now they caught this one, and they all go to the other one, right? Because their policy is to go out to the closest surviving fly and take a step in that direction. Now, unfortunately, this policy is not very good, so it will take some time to complete. But eventually, the fly will not escape. The fly is moving randomly, so it may. OK, so that's it now. OK, so that's what the base policy does. So now let's see what the rollout does with all. OK, as a prelude, the cost of this base policy that follows the shortest path is 85. Now, the all-at-once rollout, where we optimize over the first simultaneously, over the first step motion of all the spiders, takes 34. The one at a time also takes 34. And this is something that we observe here. Much greater reduction over the base policy. And you're not hurt too much by doing things one at a time versus all at once. And of course, here it's 125 move choices per step. This is only 15. And this is only because we have 4 spiders. If you had 10 spiders, it would have been, the difference would be much larger. So let's see what happens. OK, so the spiders are right in the middle, and there are the 2 flies at the end. And what you would like to see is the spider split. You don't need all of them to go to 1 fly. You send 2 this way and send 2 that way. So that would be something intelligent to do. The other thing that would be intelligent to do is having 2 spiders go at a fly. They will try to encircle it somehow. They will not go straight to where it is. They will coordinate and try to encircle it. And indeed, Rollout does that. OK. They split off, but they don't go in unison. OK, they try to do something like an encircling motion. OK, this does not show very clearly here. OK, so the first fly was caught, and this one slowly started going in the other direction, but it didn't try too hard. And the reason is that it figured out that there are 2 spiders out there. They're going to catch the fly before I have the chance to get there. Okay. There's also Monte Carlo simulation involved here, so there are some slight errors. But the rollout is far more intelligent than the base heuristic. And this is the one at a time. Basically, it does the same similar things. Again, the spiders separate, and they go towards different flies, and they try to do some form of encirclement of the fly. Here it's caught, and it's OK. So that happened pretty quickly, and the cost is 34 in both cases. In some cases, you see one type of policy do better, and in other cases, the other type of policy do better. And there are also some theoretical analysis on simpler problems that sort of verifies this behavior. I think that what you see here is pretty close to optimal. It's not quite optimal, but it's pretty close to optimal. OK, what are some of the issues in this multi-agent parallelization? First of all, the one-at-a-time rollout and the all-at-once rollout produce different rollout policies, and one may be better than the other depending on the problem. How about doing one at a time, look ahead in the context of policy iteration? Will exact policy iteration also work? Well, the answer is no. One-at-a-time rollout used repeatedly may stop short of the optimum. I mean, one-at-a-time rollout is like coordinate descent, where you go try to reduce the cost along one component, and then you try the second component, and so on. And we know that coordinate descent reduces cost, but it may get stuck short of the optimum. This can happen here also. However, when approximations are involved and randomization, this phenomenon of getting stuck just doesn't happen too often. Okay? And we speculate that an approximate policy iteration, one at a time rollout, will often perform about as well as all at once rollout. And the order also may matter here. So this is all in the realm of speculation at this point. This has to do with faster computation of the one-step look ahead, but where is the parallelization? Of course, you have multiple decision makers, multiple agents, and each one has computation capability. You may give them some autonomy and try to parallelize the computation. And one possibility here is divide the agents into coupled groups. And there is coordination within the groups, but less of a coordination, less communication among groups. So for example, I mean, these spiders here don't really care what these spiders do, right? So they don't need to coordinate their actions with the actions of this group. Similarly here, these two groups require less coordination than the actions within the group. So there is this possibility, and there are obvious choices, but there are a lot of interesting theoretical and algorithmic issues to be resolved here. How do we form groups, clusters of spiders or agents? You probably need to use some kind of some feature extraction to divide the groups in an intelligent way. How frequently do the groups communicate? What's the type of intergroup communication that you would like? Intergroup communication that you'd like to do? What kind of aggregated information should this group send to this group? And so on. Furthermore, there may be issues of estimation, distributed estimation, information processing, and so on. All of this is a very broad range of problems that have been addressed in the literature, but they could also be viewed in the context of reinforcement learning. Okay, now I'm going to go into my last topic. Perhaps I can take a little bit more time since Mengdi seems to be traveling still. Okay.
She'll be here at 4.
She'll be here at 4?
Yes.
You got a message? Okay. Okay, I can talk until 4. Oh, no, I'm sorry. No, okay, I can certainly talk a little more. Okay. Are there any questions, by the way, since we have some more time?
Well, there is a talk after you. Chava's going to move into that slot. So.
Okay, but Chava is in the afternoon, right?
No, he's volunteered to move.
Oh, you have more. Okay, okay, okay. Give me a little slack,
But
please.
you'll be taking it away from Chava, so you guys can fight it out.
Why don't we all take away some from Mengdi, okay? That would be appropriate. Okay, multiprocessor parallelization, the other type of parallelization that's of interest here. The idea here is that you have the state space, and you want to partition it into several subsets and construct a separate policy and value approximation in each subset. Now, it's possible to do a regular partition of this state space, like a grid type of partition, but that's not a good idea. A better idea is to use feature-based partitioning, where you have a feature vector for each state, which summarizes important characteristics of the state, and you discretize more or less regularly the space of features, and then map this partition into that partition through feature extraction. And so in each set of the state space partition, you have states with similar features. Okay, that's the idea. Put states together that are more or less similar in the sense of in terms of their features. And now there's the question of how do you implement truncated rollout and policy iteration with partitioning. Okay, there's an old and fairly obvious idea. You assign a processor to each subset of the partition. All of this is offline training. It can't be done online. It's offline training. You assign one processor to each subset of the partition. Each processor uses a local value and a local policy approximation and maintains asynchronous communication to the other processors. The processors need each other's estimates to do this their training. And we update values locally on each subset, update policies locally on each subset. You may use multi-agent parallelization on this, in this policy update, and then you communicate asynchronously the local values and policies to the other processors. Now, this obvious algorithm has been around, this idea has been around for a long time, but Williams and Bird gave a counterexample to showing that this algorithm can fail even with a lookup table representation of values and policies, and also for a deterministic problem, actually. But just there was some asynchrony. Now, my work with Jenny Yu from 2010 corrects this difficulty. We modify this algorithm so that this convergence difficulty does not occur, and we have proved convergence to the optimal policy and optimal cost function, assuming a lookup table representation for policy and cost functions, and also allowing for asynchrony. In other words, the values and policies that other processors we get from their neighboring processors could be out of sync. They could be out of date. All of this is not trivial to prove, by the way.
Can you give an idea for how you fix it? Is it just a matter of taking smaller steps? Or
How you fix what?
how you correct the difficulty?
Okay. That's okay. In policy iteration, you solve a one-step look-ahead problem. The theoretical way to fix this is, instead of looking at one-step minimization, solve a stopping problem itself, which bounds the sizes of the value function of the value function estimates, because this can explode. That's what may happen. So you introduce a certain bound, and we introduce a new type of policy iteration method, actually, which uses, instead of a standard policy improvement, it uses a policy improvement using a stopping problem, an optimal stopping problem. And okay, so this idea has ramifications also in other contexts, and there's a series of papers on that. But it's not trivial. Now, whether you actually need in practice to introduce this modification is a different story. It certainly fixes the Williams and Bird counterexamples, but I mean, these are artificial counterexamples. In practice, the standard algorithm may work just fine. And in fact, in the example, the computation study that I'm going to give in the next slide, we didn't use this corrected method. Okay, now this algorithm here that we had with Jenny Yu admits extension to neural network approximations and doesn't converge to the optimum, of course, but you can obtain some error-bound type of results that show that the method doesn't go crazy completely on you. Okay, so you can look at the literature on this. There's quite a bit. And let me give you an idea of how you would do approximate policy iteration with local value and policy networks. Suppose that you have a base policy and a value network for every subset of the partition. This is a partition with 5 sets, and within each set there is a processor that maintains a policy approximation and a value approximation. And now we want to obtain the rollout policy. How do we do that? Within each set, we pick initial states, and we run the local policy up to the point where the state enters into some other subset of other processors. Now, these processors have communicated values for these states here, and that's what the processor uses. So the processors do simulations within their local set and take value approximations given to them by other processors. Initial state, these are truncated rollout trajectories using the local policy network, and terminal cost approximation supplied by this guy here, this processor, the local value network that this guy has supplied. So it's truncated rollout using multiple approximations. And then we repeat. We update the local networks, we communicate, and so on. And I would also say something briefly for those who have some experience with this idea. A major problem with policy iteration is the issue of exploration. How do you sample the state space? How do you pick this initial stage to do your approximation and generate a training set? This is the Achilles heel of reinforcement learning, you might say. It's extremely difficult to deal with this problem. I would argue that through partitioning, you can deal with this problem better because you can control this distribution of the initial states more finely within each subset. This is something that just speculation. There's no analysis associated with this. But in experiments, we have found out that partitioning helps with the issue of exploration. OK, so this is my last technical slide. This is from the paper that I wrote with Stephanie Gill and her students from a few weeks ago. It relates to reinforcement learning for POMDP, and implements the distributed ideas that I have discussed. Okay, so this is a pipeline repair problem where you have 20 locations along a pipeline which are potentially damaged. They can have different levels of damage, but the level of damage is imperfectly known. It is known only if a repairman goes in there and does an inspection and determines that it's damaged to what extent and decides whether to fix the damage or go on, right or left, to some other location. So the number of states here, okay, we assume number of states is, okay, evolves according to a Markov chain. There are 5 levels of damage, 5 to 20 states here, okay? And the total number of states of this POMDP is 10 to the 15, it's astronomical. Of course, the real state of the problem is much bigger. It's the belief state space over these 10 to the 15 states. Okay, so the repair robot moves to the left or to the right, inspects locations and repairs them. However, it may want to skip a mild repair in the interest of getting closer to a location that needs a repair urgently. Because remember, there are 5 different levels of damage here, and some of the damage may be critical, and the repairman may need to rush there and don't waste time repairing locations where repair is less urgent. So, a huge POMDP problem, and we address this with belief space partitioning, with 6 policy networks and 3 value networks. So the state space is partitioned in 6. Okay. Why 6 and not 60 or 600? Because even with 6, the computation time was very large. We're talking about serious computations that run over days, okay? The problem is stochastic, it involves Monte Carlo simulations, and so on. However, we did get some success. And okay, here you see some graphs. This is the performance of policy iteration. The starting policy, I'll tell you what that is. After iteration 1, after iteration 2, 3, 4, you have steady improvement. Depending on how much approximation you have, you may get better or worse performance. So the blue lines correspond to 6 policy networks and 3 value networks. The red corresponds to no value networks, just untruncated rollout, basically, with 6 with the state space partitioning in 6. And the yellow corresponds to no parallel computation at all. So you see that the more you introduce approximations, parallel computation, there is a deterioration. However, it is not, you still do much better. And we compared, by the way, our method with some standard POMDP methods. There's a method called despot that people talk a lot about. And I can't remember the authors, many authors. And there's another method called POMCP. And again, it has 3 or 4 authors, and one of them is David Silver. And they implement, they try to address large-scale POMDP. And we tried their methods with our problem, and we found out that actually their methods work worse than the base policy. They involve all sorts of approximation. Despot involves pruning the look-ahead tree. And how you prune it, we prune it in many different ways. We tried many different hyperparameters. We never got it to work better than the base policy. The same thing with POMCP. POMCP uses a Monte Carlo tree search, and again prunes the look-ahead tree in some randomized way. And again, we couldn't get it to work better than this. Okay. Now, what is this policy? This policy is a greedy policy that sends the repairman to the closest damaged location. It goes to the right if the closest damaged location is to the right, or goes to the left, and always fixes a repair when it gets to it.
Regardless of urgency. Regardless of the urgency level.
Regardless of the urgency, yeah. If it's damaged, okay, one of the 5 levels is not damaged. If it's damaged, then you fix it. That's the base policy. Yeah.
Can you remind us what's not observed? Like what part of the state is not observed?
I'm sorry?
What is not observed?
What is not observed?
Right?
The state of repair, of the state of damage of its location is unknown, and it evolves according to a Markov chain.
But you know the location of the damages?
You have an a priori probability distribution over the 5.
I understand the greedy policy, like how does it work? The initial policy.
Okay, you start at a certain location, you look to the left and you look to the right, and you figure out where is the closest damaged location. It has some damage, and then you go in that direction. So you may go in this way, fix some damage over here, and then go back, fix some damage over there.
Lifting this damage. Yeah.
Yeah, but now the observations are when the repairman goes to a location, it finds out exactly its level of damage. Okay. It observes the level of damage exactly. Otherwise, it's unknown. Okay. And also, we assume here that one is fixed, you stays fixed. So there's an estimator here, a belief estimator, that uses the observations, the inspections of the repairman. Okay. So I can give you offline details of this implementation.
Is this like somehow like a non-convex optimization problem with a couple of like local minimums and a global minimum? Is this something like that?
It's a horrible optimization. Convexity is a dream beyond the reach of the wildest fantasy.
Yeah, like a non-convex.
Here we're using, these are neural networks. They involve quite a few nonlinear units, and their cost functions are highly non-convex, and they are trained with off-the-shelf software. Okay, there are off-the-shelf software. We use off-the-shelf software. Presumably, if you had your special software, you would do better, but still, there's no convexity, there are local minima, there are gradient methods that crap out on you most of the time, and so on. Okay. Okay, so my last slide. Obviously, And it's generally accepted that reinforcement learning is a very promising but also very computationally intensive methodology. And parallel asynchronous computation is an obvious answer. It has been the answer for AlphaZero, in fact. So it's important to identify methods that are amenable to distributed computation. And one-time rollout, just a single policy iteration with some base policy and multi-agent parallelization and value and policy networks is well suited to exploit parallel computation. And rollout generally is often easy to implement and is typically reliable. As I look into this landscape of reinforcement learning methods, I find only one method that's reliable, and that's rollout, in my opinion. It works every time, okay? It may not work spectacularly well, may not improve the cost function spectacularly by spectacular amount, but it works, okay? It never gives you worse results. And it works similarly from one run to the next. If you go to some of these other methods, you'll find that more than half the time they don't work. Or if they work, it's, okay, if they work, they are not also easy to fix. With rollout, it's relatively easy to try to figure out what to do. There's so much opaqueness in some of these reinforcement learning methods that okay, you often find yourself trying to blindly trying various things and hope that some will work. You may have a different experience. That has been my experience. But rollout is quite reliable. Repeated rollout now, multiple policy improvements, is much less reliable. But hopefully that with partition architecture and multi-agent parallelization, you can get faster convergence, and it's more ambitious but more complicated. The first talk dealt in part with model predictive control. Rollout contains, as a special case, model predictive control. So a lot of the things that I've discussed here may have some connection to model predictive control, although typically model predictive control has continuous state spaces. It doesn't have, so that's an important difference. Rollout also has many applications to discrete combinatorial optimization problems, like routing problems, scheduling problems, multi-assignment problems. And this is, in my book, this is dealt in considerable detail, although I haven't dealt with this at all. But the rollout ideas are relevant. And needless to say that there are so many interesting analytical and implementation challenges here. So thank you very much.